Okay, then welcome everyone, especially welcome to the 2 students in the room. And I'm not sure, there are also, I think, 4 people connected online. So yeah, my name is Matthias Magdowski. I'm a curious QSPICE consultant at the Otto von Guericke University of Magdeburg in Germany. And there's someone saying hello from France in the chat. So this is also nice. There I've been not the week before, but 2 weeks ago for some teaching exchange. But the topic for today is QSPICE. So I will, as usual, already share my screen. And hopefully this should work. So yeah, the idea is to give some introduction, some brief workshop on electric circuit simulation with a software that is still quite new, I would say. It's this QSPICE. And before we start, I have a survey for you. And okay, we are just these 2 people, but maybe it's also interesting for the people online. So it would be great if you could scan this QR code with your cell phone and go to this website, and then there should be a survey. I will also go to the website in a second. There should be a survey that asks how many circuits have you already simulated in your life. And there's still some cell phone pointing at me, so I will wait a bit more and then go over to this website. And there are 3 people connected. And there should be some question series somewhere that asks, I've already simulated so many circuits so far, and we have 1 answer already. Does it work for you? Does it work for you? Does it, do you feel, yes, it's working? It's working? You're just giving the answers, okay. So there's 1 people not participating in the vote. Okay, so I will. Okay, so there's one person that says 0. I don't know if for the people watching online, of course you can also just write something in the chat if this does not work for you. You need to find the QR code once again, right? And I see in the for the online people, it's maybe difficult because I might better switch over to this one here, because then the full QR code should be visible. So let's wait for 10 more seconds or so. As said, you can also write something in the chat, just to give me some idea how many am I talking to total newcomers to this topic, or do you already have some experience in circuit simulation? So, but we still have just 1 answer, and this 1 answer says no. Okay, so I will stick with this. By the way, there should be also some Q&A thing there. So especially for the online people, you can also paste in questions there if you like. In the room, of course, you can also just ask in the room if you have questions. But this is always difficult for the online attendees. Okay, so let's assume no one has any experience with circuit simulation. Now we can start with some motivation. And the motivation is usually, as electrical engineers, and you are studying electrical engineering and information technology, you as well, we are interested in analyzing the behavior of such circuits here. So what does this circuit do? Do you have an idea? So we have some AC source on the left. We want to have some DC voltage on the right. And we have 4 diodes in between. And these diodes behave, or what is the purpose of these 4 diodes in this bridge configuration? It's an H bridge and it's a rectifier bridge. Yeah, and it somehow works in this way. So if we, let's say by hand, somehow try to analyze the circuit, let me try to make a screenshot of this, if I remember. What was the corresponding? This was the keyboard shortcut. So let's paste it into my drawing program. So let's say if the source voltage is positive, maybe let's take red, a red color for this. So if we have a positive current, a current going in this direction, then current will go via this diode. Then it will go in this way through the resistor, of course will also go here in this way, will return here, and will return via this diode back to the source. So we have a current path along this way. And if we would have a negative voltage and therefore also a negative current, let's use blue for this. So a current that is pointing here in this direction, this will go upward via this diode, will also go downward here, and will also return here this way, and then return via this diode, and will return this way. So we get a current loop that goes like this, and then returns this way back to the source.
But they use the diode for.
Say again?
Like I'm saying, why? Yeah.
This diode is for the return of the positive current. So as we can see, in each cycle, 2 diodes are used, and I mean the diode is like a valve for current and charge, and so there will be only current going in the direction of the diodes. And as we can see, from some AC current on this side that has opposite directions, we make a DC current on this side. And this current here will of course have the same shape as the AC source. So this would be positive and negative and positive and negative, and here the voltage would then just be positive. And so what is the purpose now of this capacitor here? To store energy and to somehow smoothen the output voltage. So at the beginning we need to charge the capacitor, but then it will slowly discharge and charge and slowly discharge and charge, and we get a kind of flat output voltage. And some usual question would be, what happens to the output voltage if we change the value of this capacitor? And if we would use a larger capacitor, it should be more flat. And if we have a smaller capacitor, it should fluctuate more. And this question, to be honest, is by hand kind of difficult to solve. If you would like to calculate this without the help of a computer, I would not say that it's impossible, but it's a quite challenging task to do so. And so this is my intro, my motivation example here in this QSPICE already. So here I've already built up the circuit, and I will click on this run button to simulate, and then some result should show up. So I will move this to this side and move the result to the other side, and then maybe add a grid. And then we can see how the output voltage, now what I've plotted here is the output voltage as a function of time over 5 periods of the mains grid voltage. This is 50 Hertz, so we have 20 milliseconds of periodic time. And we can see how at the beginning capacitor needs to be charged, and then for the smaller capacitor, for the 1 millifarad, we get a larger ripple. For the larger capacitor, we get less ripple. And as said, now this is a very nice, efficient way to analyze such circuits, and it will be very, very challenging by hand to calculate something like this, because we need to do a transient analysis. We would need to solve differential equations in time domain, and we have these nonlinear elements. We have the diodes. So, some intro. This QSPICE is a relatively, as I said, relatively new SPICE variant. This SPICE is something very, very old. It's some kind of backronym like laser. Does anyone know what laser stands for? Yeah, something light amplification by stimulated emission of radiation. This is what laser stands for, and SPICE stands for simulation program with integrated circuit emphasis. So some simulation program where you can simulate circuits. And this interestingly has been developed, I don't recall at which university, but in a student's course. So there was some professor who was aware of electrical engineering and computer science, and he knew, okay, now we have one of these very powerful and big computers at our university, and what can we do with this computer? Let's use this computer to calculate, to analyze circuits. And of course, at this time, computer had no real, you would need to have these punch cards to program them. But in a course with students over a semester or a year or so, they developed the very first circuit simulator and called it SPICE. And then there are very, very many SPICE variants, and this QSPICE is from a company called Qorvo, and Qorvo is an US-American manufacturer of semiconductor components and circuits and devices and stuff. And they give out this program. I mean, I have it still open here a little bit as an advertisement for their components, because as we will see later on, you don't just find here the basic components like a capacitor and like a diode and so on, and some behavioral circuits for analog and digital stuff. You also find components of this Qorvo. And so the idea is, okay, you want to build something, you simulate it with the components of Qorvo, you find out, oh, it's working in a simulation, then let's also buy the components there at this company. And that's why they give out this program for free. You can download it at this website. I think also qspice.com would also work, but it also just points to this website, and this is the logo of this QSPICE. As it's a relatively new program, it will just run under modern operating system, and unfortunately it only runs under Windows. And you need to have a Windows 10 64-bit edition or Windows 11. I think all computers that are able to run these operating systems will have at least 4 GB of RAM. I've really checked when I install it, it consumes 100 MB of disk space. I'm not sure. I think this is, if you really want to do some serious simulation, then you probably need to have these 60 GB of disk space. Not for the simulations that we do today, yeah. But the thing is, of course, if you have complicated circuits and if you simulate in time domain, so with very many small time steps, and for each time step you save all the currents, all the voltages in the circuit, then of course and this without any compression, then of course it will consume lots of space on the hard disk drive. So what is nice about the software, it's freeware, so you can use it for free, you can download it for free, as you've just seen, and you can also use it for commercial purposes. It's not an educational license, or not a student license, or not something that can only be used for academia and research. You can also use it in a company for free. And I think that many companies do this. But it's closed source, so you cannot really look into the program what it does. And this is sometimes, of course, a pity if you want to do research, because then you would like to know what exactly the program does here and there. But okay, I mean, there's no free lunch, as the Americans say. So in comparison with other SPICE derivates and circuit simulation programs, it's said to be, as said, my experience is rather limited with the software. It's said to have a very high speed. So what I've read in forums was that it's, let's say, 5 to 10 times faster as if you would do it in other SPICE variants like LT-SPICE. Yeah, and it should be very accurate and reliable because it's based on the 64-bit floating point operations and so on. It's mainly focused on power electronics, so it's quite simple there to create MOSFET, IGBT, JFET and diode models and stuff. And I mean, this is what I've read on the website. It said that it should be able to create high quality, publication quality graphics. To be honest, I would doubt this a little bit because I do all my stuff in LaTeX. But what I've checked, at least, that it's very simple to export results and to import them in MATLAB, in Octave, in Python, also in LaTeX should be no problem. But maybe, I mean, we have this plot here somewhere open. We could check what happens if we print this or export. We can export data. I'm not sure how you could from this create the publication quality figure. But at least you should be able to print into a PDF file, and it's a vector graphic and it should not look too bad. So this is the maintainer of this program, Mike Engelhardt. He's also very active and attending lots of conferences. Unfortunately, I have never met him in person. So this would be something on my bucket list. No, he's also from the United States. His name sounds German, but I think he's some American guy. Always wearing this hat and this iconic blue tie. So there's also another picture of him here with this QSPICE. And so he's also doing lots of conference talks and workshops and stuff like this. And yeah, and interestingly, since 4, 3, 5 years or so, he's developing this QSPICE, and he was also developing this LT-SPICE before. And as said, the previous workshops that I've done were all based, this was my Wacom tablet, but this is solid, all based on LT-SPICE. And so I think this is a picture from approximately a year ago, where I've also stood here with a little younger version of me, with a different shirt, but with the same camera and same recording setup and so on. And I was doing some LT-SPICE workshop, and I was posting, as you mentioned, I was posting something on LinkedIn, and I was also mentioning Mike Engelhardt. And so then from my point of view, something very nice happened, because Mike Engelhardt himself commented the post and said, yeah, you know, this LT-SPICE, I've developed it long time ago, but you should try QSPICE. This is new cool stuff. And so that's why I'm standing here today giving a QSPICE workshop. So the post can be found there.
So like this is the reason behind to start.
Exactly. This is more or less the reason why I'm doing not an LT-SPICE workshop anymore, but because I'm doing QSPICE workshops. Okay, so as we want to simulate circuits now, this is very similar to all other SPICE variants. If you want to insert numbers to parameterize the components, you can use integer numbers. You can also use floating point numbers. And I mean, for you, it's totally natural. For the German students, it's always very confusing that they have to use a dot as the decimal separator and not a comma. And you can also use this scientific notation with the power of 10 thing. And you can also use these scale factors like, so this here everything here would be the same number. So 1000 ohm or 1 kilo ohm, and or 1K0 is also 1.0 kilo ohms. You have to be careful a little bit because it's not case sensitive. So if you want to use 1M for mega, it will not give mega, it will give milli. If you want to have mega, you need to use 1 meg ohm. This has caused lots of confusion, to be honest, because I know people wanted to simulate something in the megahertz range, and then they simulated in the millihertz range and got, of course, totally wrong and confusing results. And you don't need to write ohm and Henry and farad. And this also sometimes happens that people want to say something like, I have a 1 farad capacitor, and then they write 1F. But 1F is 1 femto. It's 10 to the power of minus 12 or minus 15, something like this. 15, I think. Yeah, and so then if you want to have 1 farad, you just need to write 1. And there must not be a space between the number and this prefix. Otherwise, it won't work. So no space allowed. Okay, and then I have a second survey for you. Namely, you can go, if you are still on this website, it should be the very same QR code. And maybe you have already filled this out. Maybe I can shortly remove my camera window. So to make the full QR code visible also in the recording or on the stream, I think it should be the same thing. Then it should be just the next question. So I will go over to the website if I find it back. So it should be here. And yeah, so that's right, because maybe, this is always confusing me. It says it's locked, right? Präsentation verlassen. Workshop. No, now it should work. What other programs do you know for, or do you use for circuit simulation? It should be just on the question series, the second thing. Okay, so there is, okay, LTSpice, MATLAB. I've not heard of power word simulation. I would need to check this up. And there was this Verilog mentioned. To be honest, I've also never used this. This is really for electronics, right? And for flip-flops and digital mixed signal. Okay. I know that it's, if we check the help here, as said, my experience is kind of limited, but that there is some Verilog capability also in QSPICE to somehow combine these two together. Okay, so on my slides, I've listed some more examples. So I would say the most famous one is QSPICE. That now belongs to a framework called ORCAD that somehow belongs to a company called Cadence. And it's a huge program, and it also requires a license. And we have just used it because one of our industrial partners and customers used it. But yeah, also my experience there was mixed, let's say. So what I've really used a lot in the past was LTSpice, as said, because it's also freeware, not open source, but a very small, but for this very powerful program, and you can do a lot of stuff there. And there I really have a lot of experience, I would say. And there's a question.
Have you heard about the PSCAD?
PSCAD, yes. I think this is also for power electronics stuff, I would say. But I think I've never really used it. Yeah, so this is very large. This is very small, still very powerful, but they require some installation on a computer like QSPICE. So this Easy EDA is a nice thing because it's like the Google Docs for the overleaf. What overleaf for LaTeX is, it's some online circuit simulator. And so you just go to the website, and the solver that they use in the background is also LTSpice. But it's just some online interface, let's say, for some LTSpice solver, and you can draw circuits there online. You can share them with colleagues and friends and fellow students, and do save projects there. And then the idea, or I think their model, is also that you can also design printed circuit boards there, buy components and stuff. But it's also closed source. You cannot really look inside there what's really happening. And so the last thing, this QUX or QUX, is some abbreviation for Quite Universal Circuit Simulator. And yeah, it's, as the abbreviation mentions, it's a quite universal circuit simulator. This is really some open source project. As for many open source projects, I think people that actively develop it are a bit missing. And I think it's somehow stuck in some early versions since 2017 or so. But it's kind of usable. And the advantage there is that you can really look into how it's working, which is, as said, interesting for research or if you want to do comparisons and stuff. And what's also very interesting about this Cooks is that they have a very, very nice manual, a very long PDF file, I think 200, 300 pages, where all the theory is also explained. So if you want to know how this all works in the background, you can look into this manual. And this manual, of course, also helps if you want to simulate for whatever reason, if you want to program for whatever reason your own circuit simulator. So I have been doing lots of EMC analysis with field coupling to transmission lines. And then it was always very challenging to get this field model into some circuit simulator. So it was much easier to program my own simple circuit simulator that I needed for my purposes and then include it into MATLAB and couple it with my field simulator, for example. And so stuff like this would be also possible here. But I have also coupled MATLAB with LT-SPICE. I think it would be also possible to couple MATLAB with QSPICE. And as mentioned, it can be combined with this Verilog. It can be combined with C++. There are lots of... and Python, there is also, I've just checked when I prepared the slides, there's also some, on GitHub, some, I don't recall the name, but some Python QSPICE coupling module. To do, for example, advanced analysis, we will see later on that it's not easily possible to plot Nyquist plots, for example, in QSPICE, but it's quite easy to export the data into Python, do the plotting there, for example, or into Octave and do the plotting there. Okay, so then we can take a look at how does it work. And why do we do this? Because there's this problem of every simulation that you may have encountered or may not. And the problem of every simulation is garbage in, garbage out, or bullshit in, bullshit out. Yeah, you need to, if you have a problem that you want to simulate, you need to tell the simulator the problem in the right way. Yeah, and for example, if you confuse milli and mega, then it won't work. And then you will get some results, and you also need to interpret the results in the right way. And the problem, if something fails, the computer will always calculate right, let's say. And if something fails in the simulation, the problem is often sitting in front of the computer, as one says. Okay. So that's why we will take a look at some very, very simple example at the beginning. Just take a current source and have 4 resistors. And so 2 of these resistors are connected in series, and 2 other resistors are connected in series, and then these 2 branches are connected in parallel. And let's assume that all the resistors have the same size, and that, for example, here we have 1 ampere of current. So what should happen? So all the resistors have the same size, and we have, for example, 1 ampere of current. What should happen? How large should be the current in each branch? Should be the same, right? Current, if this is, let's say, 10 ohm and 10 ohm, and here then we have 20 here, so current should split up equally. And if we then have a voltage drop across these resistors, and if, let's say, this here is our reference point at the bottom, and if we compare this voltage across this element and the total voltage, what should be the relation between these 2 voltages? The total voltage should be twice as large, or this partial voltage should be half of the total voltage, let's say. Okay, and of course, if the resistors are not equal in size, stuff gets more complicated, but let's stick to this very simple example. And so if we would like to calculate this, we need to have some method for calculation, and what the SPICE uses in the background is nodal voltage analysis. Have you heard of this in your fundamental study courses? Yes. And so the first step that we do there for nodal voltage analysis, we number the nodes. So we set this as as a reference node. And then we say, okay, this is node 1, node 2, node 3, for example. Okay, and so if we have done this, the next step is to set up some system of equations. But okay, let's do some intermediate step. And we will come back to this also later. Now, to explain a computer this problem, and imagine, like 50, 60 years ago, when computers had there was no mouse not yet invented, and so you had to program the computer by a punch card. There should have been some option how to tell the computer how the circuit looks like. And so one way is to use a netlist. And this SPICE netlist format is still also used by QSPICE. And in this netlist, it's just a list of all the circuit elements and then the nodes where this circuit element is connected and the value. And so if we have a current source connecting node 0 and 1 with 1 ampere, it would look like this. And if we have a resistor that goes from node 1 to node 2 and has maybe 10 ohm, then we have a resistor connecting node 1 and 2 with 10 ohm, and so on. Okay, so then if we have numbered the nodes, we can introduce nodal voltages. This would be always the voltages connecting a certain node with the reference node. So if we have 3 nodes, we have these 3 nodal voltages, and then we can set up some system of equations. This is what we would do if we would do the calculation by hand. And that is what is also done in the background in the circuit simulator. So this is what is happening when SPICE, QSPICE, LT-SPICE, whatever calculates the circuit. And do you somehow remember the rules how to set up this system of equations for nodal voltage analysis? So there's one rule that says on the main diagonal. Exactly. So on the main diagonal, there's always the sum of the elements at each node. So if we check at node 1, we have resistors 1 and 3 connected. That's why here we have 1 and 3. On the second node, we have 1 and 2 connected. That's why we have 1 and 2. On the third node, we have 3 and 4 connected. That's why we have 3 and 4. Entering and leaving, yeah. All resistors that are connected. And so the G are the conductances of these resistors. And so on the off diagonal elements, we always have the connecting resistors. So between 1 and 2, we have R1. So they are always negative, minus G1 in the, let's say, first row, second column, first column, second row. Between 1 and 3, we have this element. That's why we have it here and there. And between 2 and 3, we have nothing. And that's why we just have the 0 there. And so on this side, we have the sources. These are just the sources connected to each node. And we just have a source connected to node 1. So that's why there's just this IQ at, Q has nothing to do with QSPICE now. It's the German abbreviation for source, Quelle. I've not translated this. I should translate this. And so this is what we know. This is the right side of our equation system. We know this matrix with the coefficients, and we can calculate the unknown nodal voltages. And so for this, okay, we need to have some values, 10 ohm, let's say, 1 ampere. Then we can convert them into conductances, 0.1 Siemens, and insert this into the system of equations, and then just solve the system of equations. And then we get these nodal voltages, and this also somehow, so this is the voltage at the first node, at the second node, at the third node. And if we go back, we can also check here. If we go back, this also somehow makes sense. If we have 10 ohm and 10 ohm in series, we get 20 ohm. We get 20 ohm here, 20 ohm and 20 ohm parallel gives 10 ohm. So 1 ampere of current going through 10 ohm of resistance gives 10 volts of voltage. And so the total voltage will be 10 volt and the partial voltage will be 5 volt. So this totally makes sense and works. And so now the first task, the first idea is to simulate this example in QSPICE. And so I will move over to QSPICE. I will say I want to have a new schematic. And then some new window opens up. And yeah, I think now it's a bit challenging to make this fit on the very same screen. I won't try this. So I will just enlarge this, because then I have more space here. And you have QSPICE installed and open, so you can also try it out yourself. So the first thing, I will close this. The first thing that we need to have is the source, exactly. And this is what we will find in the built-in symbols, native devices, and a current source is I. And so I think you always need to double click on this, and then you get like a current source mouse arrow symbol, and you can place the current source somewhere on the canvas, let's say, or on this still empty schematic. With the mouse wheel, you can zoom in and out. With the space button on the keyboard, you can always like center and zoom to fit. If you are somehow lost in your circuit, if you want to go back to the home view, you can always press space on the keyboard. Okay, so then.
In my company, like how based in this with the command box?
So you need to double click on the current source, and then you get it like this, and then you just click. Okay. And the other option, I think, is you can also just press I on the keyboard. And with the I on the keyboard, you also enable this current source symbol. Have you clicked on new schematic before? Maybe you have not opened up a schematic yet. This is some usual problem that I think was also present. Okay. So yeah, now I have two current sources. So with delete on the keyboard, if you hover the mouse on this, press delete on the keyboard, you can also delete current or sources or other elements. Okay, so then we need to have resistors. Resistors are called R. There's the USA style symbol and the UK style symbol. I will decide for the more familiar for me European style symbol. So double click on this and we can have 1, 2, 3, and 4 resistors. And with escape, once again, we get out of this mode. So then the next thing is we need to wire this together, and the wire tool can be found here under edit and then draw a wire, or you can also press W on the keyboard and then you get this wiring pen, let's say, and as usual I will wire the outer circuit together. Go back to the source and then do this inner connection here. So from this resistor to the other resistor. And then you can see once you really connect them, let's say these soldering pads will disappear. And if you create a node, then some node or some junction will appear. Okay, so then the next step is all these components need values. So we can just click on this, edit this attribute, or do a double click and say here we want to have 1 ampere, here we want to have 10 ohm and 10 ohm and 10 ohm for each of these resistors. How to delete stuff? Just do a double click on this field, or use the alternative mouse button and say edit this attribute. So now all the resistors are 10 ohm and the source is 1 ampere. Then we also need a ground node. what is like the reference node for the nodal voltage analysis or modified nodal voltage analysis. And the ground node can be found here with place ground or with the G button on the keyboard. I will connect the ground node there, press escape. I will wire this together here. So this is the ground node. Now, if you check this lower left corner in the program, then it says this is ground, and it automatically numbered the other nodes. So it's saying this is the wire N01 in my case. This is the wire number 3, because this is the one that I connected the latest, and this is the wire number 2. And there, so this is now a bit in contradiction to how I labeled them in my example here. So there's a way to manually number them, and this is called place a net name, or with the N button on the keyboard. So I will just put one here, press N on the keyboard, put another one here, press N on the keyboard, put another one here, and now say this is node 1. Just double click, this is node 2, and this is double click, this is node 3. And now if you once again check the lower left corner in the graphical user interface, it now says, okay, this is wire 1 or node 1, this is wire 2, this is wire 3. So they have exactly the same names as in my example here. Okay. So then we would like to simulate, right? And starting the simulation works with this run button here. So we can click on run, but then there's some fatal error that says, I have not found some analysis command, and you need to add the SPICE directive, such as Tran, for example, that will do the simulation for you. And so from my point of view, this is something that for newcomers must be totally confusing in this program. That there is no button where you can like select what type of simulation you want to have. So you would need to check the documentation, and you would need to know a little bit, because what we would like to do now is called some operating point solution, which is here, bias point analysis or DC operating point solution. And so we need to have this command. So we say now we want to have this, we want to place this SPICE directive and at this .op. And this does calculate some operating point. Okay, so before I click run now, what I would like to show is, where was it possible to do this? View. Here. What I would like to show is this netlist. So if you go to view and netlist, it will open up a small editor. And in this editor, you can see this netlist that I've just mentioned before. Right, the very same example like here, that we have a current source connecting these nodes, we have a resistor, or we have these 4 resistors connecting these and these nodes with these and these values. And which is just another representation of the schematic, let's say, or of this circuit. And this is, from my point of view, very, very interesting and very, very useful, because you would not need to draw the circuit by hand. You could also just write down a netlist. And now you might ask, okay, but why should I not draw the circuit? Why should I write the netlist? Because sometimes you might have very, very complicated or very, very long circuits. If you want to simulate a transmission line, it's always something like you have some per unit length. Let me switch to full camera view. We have some per unit length inductance, and then you have some per unit length capacitance, and some series inductance and some shunt capacitance, series inductance, shunt capacitance, and so on. And so if you want to have 500 elements, you don't want to draw 500 elements by hand, but it's very simple in MATLAB, in Python and whatnot to write a program that gives you this netlist, import this netlist, do the simulation. That's the big advantage of that that this solver can still handle these netlists, and you can just operate with netlists. Okay, so now we can click simulation, and then this is also from my point of view not the best solution, because we have now calculated one operating point. Still, it will open up a figure, even if we don't really want to have a figure in the sense. We just want to have the list of the voltages. So you can go to File in the figure and you can say Export Data. And if you go to Export Data, then it will show you the result. And now we could check. So it calculated the 3 voltages. And the 3 voltages, if I go back to my slides here, these are exactly the same voltages that I've also calculated by hand here. So this somehow works nice. I'm not able to enlarge the figure. Now it's working. Yeah. So there are all 4 voltages, and we said, okay, if we have the 1 ampere current, it will split up. Half of the current is going this way, half of the current is going the other way. Then we also have 0.5 ampere of resistance of current going through each of the resistor. So now the question is, let me close the door. Now the question is, why are these currents negative? I mean, no, this is now really the current at the end. It's not this diagonal element here with the conductance. It's that the current has been calculated negative and not positive. Like a negative current. Why is the current negative? This is, from my point of view, also still not optimum. I mean, now once it's simulated, I think we can also, why it's not working, it should be symbol properties, raw attributes. Yeah. So, okay, now we can see if you hover the mouse over the wire, now we get the voltages. So you have 10 volts here, and we have the 5 volts there and 5 volts there. And we can see that in this resistor, 500 milliamperes are flowing in at this side, and minus 500 ampere are flowing out on this side. But this is counted as the positive current. There's no sign before the current. This is counted as the negative current. And so the thing is, I'm not sure how to change it now. But if we, and the power is also calculated. So I think we would need to rotate the resistors. But I'm not sure how to. Okay. I think it works like this, but then all the wires are in the wrong way. So let's do it at least for this side here. So I will delete these wires. I will also delete this wire. Take this resistor. How can I? As said, my experience is still very limited. Why can I not maybe use this? Why can I not rotate this resistor? It worked when there were wires connected. Okay. I think you have to click at the same time and then it will somehow rotate. Okay, so now I've rotated resistors. I will wire everything together. And then at least for the resistors 1 and 2, if we repeat the simulation, and this is what I also mean with garbage in, garbage out. So now if we repeat the simulation and check our results, and I think I have to close this and export the results once again. Yeah, now we can see, okay, this somehow worked. Now the currents through the resistor 1 and 2, they are positive. They are counted positive. Because obviously the usual resistor, if you just place it, the current is counted upwards and not downwards. So if before placing the resistor, if you want to have the current pointing downwards, you would need to rotate it by 180 degrees with Control R on the keyboard. And so
Can we just the source?
we could also just rotate the source. I think this should also work. But then the voltages will change, of course. So it's somehow better. And I've not found out how to move these elements without. Okay, so but let me also rotate the other ones here and then wire them together, and then everything is in order, let's say. And then all currents should be counted positively, because we will more or less just continue with this circuit. So save, run, just run. And go back to the results, maybe close this export window here because it's not yet updated, export again. And if we do so, now all currents are positive. This makes sense. And this is what LT-SPICE doesn't do, but here also powers are calculated. As said, it's a program that is mainly used for power electronics, and then people are interested, what would be the losses in my resistor there or in my load? And so we can see, okay, total power from the source is 10 watt coming out of the source. In each resistor, 2.5 watts are dissipated. Okay, excellent. So we have successfully mastered the first example. Very nice. With a DC operating point solution. So now the next step, what students also learn in Fundamentals of Electrical Engineering, is AC analysis, going into frequency domain, doing calculation with complex phasors. And for this, of course, it would be somehow meaningful if we change the resistor into a capacitor, and for example, also if we change the current source into a voltage source. So let's go step by step. Right, the voltage here was 10 volts. So if I delete the current source and add a voltage source, and I will just use this first one here, some independent voltage source, and set this to 10 volt, and click on resimulate, what should happen? We should get the very same result, right? So let's see, let's simulate. We have still 10 volts here, 5 volts here, 500 milliampere going into this. Nothing changed. Okay, so now if I delete this resistor, and this is now some huge advantage from my point of view. If we go to a capacitor, and if we insert the capacitor, it has exactly the same size. This was different in LT-SPICE. In LT-SPICE, the capacitor was always a bit smaller and you would need to rewire. Here you can just delete some element, insert a new element. And in my example here, it should be 1 millifarad. So let's also use 1 millifarad here. Okay, and if I just click simulate, now what should happen? What would you expect? Yeah, so if I don't change anything at the simulation setup here, we still calculate a DC operating point. At DC, the capacitor behaves like, yeah, it's charged once, but then once it's fully charged, and if the charge does not change anymore, then there will be no current flowing, because current is the time derivative of the charge. And so once we reached full charge, current will be 0. And so we can have a voltage across this element because we have a charge, but we have no current. And if we have voltage but no current, it's like an open circuit. So the capacitor will behave like an open circuit. So if we simulate, and if we check, of course, we still have the same 10 volts here. We have the same 5 volts here, but we get 10 volts here, and we get no current here. Of course, we get some current, but it's really, really small. It's some femtoamperes. It's, as said, 10 to the power of minus 15 or so ampere, because nano is 10 to the power of minus 9, pico is 10 to the power of minus 12, and then femto should be. So this is like, let's say, numerical noise. It's not exactly 0, but it's very, very close to 0. Okay, so then, of course, the next step is we can switch to AC. And this works by saying this is some AC source with AC 10 volts. And yeah, now, as said, this is, from my point of view, not nicely available via the graphical user interface. But here you can see there is some AC analysis, and there is some analysis with some sweep over some octave, over a decade, some linear sweep, but there's also some AC analysis over a list of frequencies. And the list of frequencies could also just contain one frequency. So if we, instead of the OP, say AC list 50, for example, we should do an AC analysis for a frequency of 50 Hertz. For one frequency. Okay, so let's run. As you can see, simulation runs super fast, but of course it's also a very simple simulation. And this is the result. And the result, yeah, this is the current, and the result is now displayed in decibels as magnitude and phase. And once again, we have just a bunch of values we want to see. We don't want to see a diagram. We want to see the data. So once again, I click on export data. And now the table, of course, is a bit different because we get these different, or we get the frequency at the beginning. I don't know why we also get the frequency once again at the end, but someone is calling. And we get the voltages. We can see the full voltage is still 10 volts. The voltage at the node 2 is still 5 volts, which makes sense. And the voltage at node 3 has some different value. And what would you guess? What is the meaning of these two columns in this table? I also needed some time to figure this out. It's because we are now doing calculation with complex numbers. It's the real part and the imaginary part. That's the idea of the two. So real part and imaginary part. And we can see, of course, the current through the first two resistors is the same. The current through the other two elements is the same. Okay. And now we would need to do the calculation by hand to check if this somehow works. Okay. But we get some result. So, yeah, to analyze this behavior of the circuit a bit more, I would not do this calculation. I would do something else, go back to my drawing program here and open up a new node. And once again, use my drawing program tablet and maybe go back to the slides, which we have here. And now, once again, copy this and paste it in the drawing program. And what I would like to draw based on this is a phasor diagram. You know what a phasor diagram is? Yes. So we will start with the full voltage, and for the full voltage, let's say the voltage of the source, I will use black. And this is 10 volts, and I will say this 10 volts are just pointing in this direction. So these are the 10 volts. So then we have the voltage across this resistor, voltage 1, and we have the voltage across the other resistor, voltage 2. In which direction should these voltages point, or how should they look like in this phasor diagram? We have two equal resistors, so this voltage should be just half of the full voltage, right? And this should be also just half of the full voltage. So because we said this is the 10 volts here and this was the 5 volts. So this should be 5 volt, this should be 5 volt, right? You're still looking very skeptical? Okay. And of course, so both voltages together should give the full voltage. So this is voltage U1, this is the voltage U2, and both together give the 10 volts or give the full voltage of the source. Okay, so now it's getting maybe a bit more complicated because we still have the voltage here, voltage 3, and we have the voltage across the capacitor, the voltage C. And so to help a bit, let's say we know the current I3, and if the current would be pointing in this direction, if this would be the current, in which direction would the voltage across the resistor point? In which direction? Voltage and current at some resistor have the same phase. And in a phasor diagram, they are parallel to each other. So the voltage across the resistor would look like this. And now the question is, which direction is this voltage across the capacitor pointing in the phasor diagram? If the current is pointing in this direction, how could you calculate the voltage across the capacitor from the current with complex phasors? It's like ZZ, right? And ZZ is, yeah, what is the complex impedance of a capacitor? 1 over j omega c times this current. And so the 1 over j is like minus j is like a minus 90-degree phase shift. So the current, the voltage across the capacitor is pointing in this direction. Still, of course, this voltage and this voltage together, they should give the source voltage. So now we would need to take this and combine it with this diagram here, right? So our, and of course, and here there is this 90-degree phase shift. So the voltage across the resistor, let's say, looks like this. And then there's a 90-degree phase shift. Oops, so this, oops. So this is the voltage across the resistor. And then there is this 90-degree phase shift, and then the voltage across the capacitor looks like this, and both together give the total source voltage, and here is this 90-degree phase shift. So this is UC. And so now, what happens if we change the frequency? If we make the frequency larger, the impedance across the capacitor should get smaller, and also the voltage across the capacitor should get smaller. So then for higher frequencies, it might look like this, that we get more voltage across the resistor, but less voltage across the capacitor. Still, both together should always give the source voltage. And so now, exactly, and the phase angle would change, and we still have this 90-degree angle here. And so now, if we would do this for very, very many frequencies, we would end up with a curve that, thanks for the comment in the chat. So if we would combine all these points, we would get this circle. So small voltages for the resistor, large voltages for the capacitor, and vice versa. And so now, interestingly, and this is really the purpose of the circuit, if we draw the voltage from this node to this node, the voltage over the bridge, let's say, then this would be always the voltage from this point to this point. Went a bit too long. Yeah, so from this point to this point, or from this point to this point, or like to here, or like to there, and so on. And then we can see, okay, this bridge voltage, the magnitude of this is always the same, right? It's the radius of the circle. And the diameter of the circle is our source voltage. So this bridge voltage is always half of the source voltage, always the same, half of the source voltage. And the phase angle changes from 0 degree to almost 180 degree. And so the purpose of the circuit that we've drawn here is like a phase changing bridge. The magnitude stays constant, but the phase will change. And so this is what we can also nicely see in QSPICE now, if we do it correctly. So we will change this list command and say now we want to have some decadic sweep. So a logarithmic sweep over a decade of frequencies. This is also written in the manual. Do I have the manual still open? No, I think I've closed it. And so a decadic sweep, let's use 100 frequencies per decade and go from 1 Hertz up to 1 kilohertz. And so now it should simulate 300 frequency points, or 301 frequency points. If we simulate, we still it's a very fast, rapid simulation, and we can check the results. And the results look like this, but this is the current. So I will delete the current here from this plot and say add plot, and this bridge voltage that we are interested in is the voltage from here to here. So it's the voltage from this node minus the voltage from this node. So we say voltage at node 2 minus voltage at node 3 and say enter. And then we get this. And yeah, so now instead of having it in dB, I would just have it on a logarithmic scale. And I would also maybe like to have a logarithmic scale for the frequency axis. Okay, and then we see, oh, this is now working really nicely, because we always get 5 volts of amplitude. Amplitude is staying constant. We get this phase shift that at very small frequencies, like we can also see here, right? For small frequencies, if the frequency is small, the impedance of the capacitor is very large, and the voltage drop across the capacitor is large. There is only few current, and the voltage drop across the resistor will be very small. So we are ending up somewhere here. We really have this 180-degree of phase shift almost. And the higher the frequency, the smaller the phase. And we go down to 0. And this is what we see here. If we increase the frequency, phase goes down. So this is the purpose of this phase shifting circuit. And unfortunately, it does not really work that we can change this. So there's a polar plot and a Cartesian plot, but there is no Nyquist plot. And that's why we cannot see this half circle. So if we would like to see the half circle, we would need to say export data, and we want to export this expression into a comma separated values file. And okay, and maybe I will not continue this because I've not prepared this. Maybe I will share some Octave commands for this later. And this plot here is also, to be honest, a bit confusing me. But it's somehow possible very easily to import it in Octave and do the plotting there to end up with this semicircle that we see here. Okay, so the next step is we could do transient analysis. So maybe before we do this, one idea would be to find out at which frequency we get a 90-degree phase shift. And we can see, so from this plot here, approximately at 16.2 Hertz or so, we get 90-degree of phase shift. Okay, so let's go back to QSPICE. And now say we don't want to have an AC source. We want to have, and the AC source is also a sinusoidal source, but we want to have a sinus source. And then you can see, okay, for the sinus, we need to say sine, the DC voltage, the amplitude, and the frequency. So I edit this and say, okay, sine, there's also some help there, 0 offset, 10 volts of amplitude. And for the frequency, I will select this 16.2 Hertz that we just found out. Okay, maybe move this over here a bit. And now we don't want to do some AC analysis. We want to do this transient analysis. Remember, this was also mentioned at the beginning. This is strangely ordered. Non-linear transient analysis. Yeah, and so for this, we need to have this tran command. Okay. So let's do some transient analysis, and let's do it in a way that we see 2 or 3 periods of the curve at this particular frequency. So from the frequency, how can you calculate periodic time? It's just 1 over the frequency, right? So if we take 1 over 16.2, this should give us the periodic time. And if we want to simulate 3 periods of time, we do it like this. And this should hopefully do the job. And let's see what it does. Click on simulate. It's simulating. There is some result. There's the result. And so here's our output voltage. Of course, at the beginning, it needs some time to charge and so on the capacitor reaches steady state, and I could also add a plot, maybe add a grid and add a plot for the source voltage. Okay, now we see it nicely works. This is the source voltage, 10 volt. Our bridge voltage, our output voltage is 5 volts, half of this, and the phase shift looks like 90-degree phase shift. So it's nicely working. Okay. And so the next step to complicate our circuit more and more, but still always have some understanding what happens there, because we check it step by step, is we introduce some resistor over this bridge, a 10 kilo ohm resistor. And so I will take some resistor. Current is pointing upwards, if I remember correctly. So I will rotate it. Current should point in to the right. Place this resistor here, and with the wire tool, wire it together. And give it this value of 10 kilo ohm. So if I add a 10 kilo ohm resistor to the circuit in this way, what would you expect? What should happen? Yeah, for voltages and currents. So we had this circuit before with 10 ohm and 10 ohm and 10 ohm and with the 1 millifarad capacitor. And now, before the bridge was open circuited, and now we add a 10 kilo ohm resistor. What should change? There might be some current, of course, flowing over the bridge, but this 10 kilo ohm is very large in comparison with the other resistors. So, of course, it changes a bit, but it should not change too much. And that's why if I click Simulate and take a look at the result still looks very similar as before. Still, this circuit here now would be very complicated to simulate by hand or to calculate by hand, because of this resistor here in the center, they are not in series anymore, and they are not in series anymore. And they are also not parallel to each other, and they are not parallel to each other because of this resistor over the bridge. But if we would go back to what happens in our nodal voltage analysis, so what happens is that we just get another element here and there. And except for this matrix and so on, the calculation stays the same. Okay, so this also works. So we can come to the last example. And instead of a resistor, let's add a diode. So I will delete the resistor just by hovering the mouse over it and press delete on the keyboard. So then the resistor is gone, and we will use a diode, and we will use a standard silicon diode. And also this with Control R on the keyboard needs to be rotated. And I mean here, maybe if I check this once again, here also, maybe this is the reason why also for the resistors, the current points upwards, also the diode. At the first, if you just enable it, points upwards. So we need to rotate it 3 times, and then the current will be able to flow in this direction. Okay, so I've not clicked on Resimulate yet. This is the result that we had before. Maybe I will move this to this side, move the circuit to the other side, make this a bit smaller. So if I click on Resimulate, what would you expect? What should happen if we now add, instead, before we had a resistor in the circuit, now we have a diode in this circuit. What should happen?
And is it just the direction will be changed? Yeah.
So the resistor before was very large. It was not really conducting any current. And if it would conduct current, it would conduct current in both directions. Now we have this diode. What does the diode do? And it said it's like a valve for currents. So we can have a positive current going in this direction, going to the right. But we cannot have a negative current going in the opposite direction, going to the left. And for a positive voltage going in the right direction, we also need to have a certain voltage drop for a silicon diode, 0.7 volts or so. And then the diode will, let's say, break through. It will get conducting. But in the opposite direction, there will be no current, but there will be the full voltage. So this is the source voltage, the dark green curve, and the light green curve was the voltage across the resistor, which was half of the source voltage, but 90-degree phase shift because of the 16.2 hertz of frequency. So now we have a diode. What happens to our output voltage? There will be no negative currents, but there can be positive currents. And if there are positive currents, there will be no positive voltage. So if I click simulate, the positive voltages for the output should be gone. Positive voltage should be limited to 0.7 volts, but we should have a negative voltage. Right? Okay, so if we try this out, there it is. Yeah, and so this is now a not too simple, but also not too complicated example that we have developed step by step, and where we would still somehow trust the result that this is the case, that this is valid, because we've, let's say, checked it step by step that this really works. And this is also, let's say, my finishing example. And with this, I would like to come to a summary and draw some conclusions. So this would be also my advice, independent of whatever circuit simulator or software you use for some simulation. Start with simple models. Yeah, try to understand them. Know what you are doing. Try to avoid this garbage in, garbage out. Always somehow question your results and try to validate them or compare them with another simulation tool, with some analytical calculation, like what we did, like with the phasor diagram here, stuff like this, or maybe with analytical formulas. And if this works, at least for the for your base case, let's say, and you get reliable results, then of course you can always extend it and make it more complicated, and still can be fairly confident that you get the right results. But I think the most common problem that people do is they start with a new software because they want to simulate some problem. They take the most complicated circuit that that they have so far, put it inside the simulator, and hope to get some meaningful result. And this will usually not work. Yeah, so I would always suggest to do stuff like this. Start with simple models, get some confidence, and it's always then small things like the milli versus the mega, the direction of the elements that you get negative current, and stuff like this. And yeah, so you need to know what you're doing. Okay, so with this, thanks for your attention, and then we still have some time for some questions if you like.